Right, so Green's theorem. Uh, so before we introduce Green's theorem, I need to introduce this notation. So, uh, do I not have a picture? I forgot to put a picture here. Okay, so this partial here, this does not mean a derivative. This is a geometric notion called the boundary of a region. So, if you have some, I should try to make it not overlap, but if you have some kind of thing like this that is filled in, the filled in thing would be called D. That would be your domain D. But then the outside, this boundary would be C. This is a simple closed curve. So I'm forgetting if I define simple. Simple means that the curve does not self-intersect. So self-intersecting would look like this. So the curve C does not do that. It does not self-intersect. This is not simple. Okay. And closed just means that the curve forms a loop. So the two ends of would meet. So simple closed curve being the boundary of some given domain D. Yeah, and the orientation of the boundary, that ends up being important for the consideration of Green's theorem. So we always want to orient our boundary in a counterclockwise fashion. That's the standard orientation in mathematics. So you want things to be oriented counterclockwise. And so it would just kind of sort of circulate around like that. All right. So now we have that, we can formulate Green's theorem. So assuming that you have D, a domain whose boundary, written like this, partial D, its boundary is a simple closed curve oriented counterclockwise. Then you have that this line integral, right, is equal to this double integral. So notice that this is the line integral over the boundary of the region, and this is the double integral that is over the complete two-dimensional domain. And that when you switch between the boundary and the full domain, you also have to change the integrand. So here, this would be, well, typically you would introduce a parameterization, so then it would be, these would be functions of t, and then you'd integrate dt, right? F1 and F2 are coming from some vector field, and dx and y are typically gotten from the parameterization. Whereas over here, well, F1 and 2 are still gotten from the vector field, but we end up taking partial derivatives and subtracting. All right, so typically the way that Green's theorem will be used is that, well, I mean, it can be used in either way, really, in either direction. But I think in the examples that I have, it's primarily that the boundary, the contour, that you'd integrate over would be bothersome to set up, whereas when you integrate over the two-dimensional region, it's easier to set up the integral for. And so you would end up rewriting a line integral, or a collection of line integrals, as instead a two-dimensional integral. Okay, and we'll see examples of that shortly. First, a comment. If you have a conservative vector field, so remember that a vector field being conservative means that it comes from the gradient of a potential function, which is this statement, then it satisfies the cross-partial property, which is this, in the two-dimensional case, right? The mixed partials are equal to each other, so this difference is equal to 0, and so that would mean that this integral is 0, which means that the contour integral is 0, which is exactly what we already know about integrals over conservative vector fields. When you integrate over a loop, the integral is equal to 0. So we already knew that, and it's just nice to kind of confirm that via Green's theorem. The next thing that I'm doing is just a little exercise to, I don't know, make Green's theorem seem a little bit more believable, because a priori it looks kind of strange that you can actually relate an integral over the region with a different integral over the boundary. It's kind of miraculous that this is the case. So let's just see concretely that this works with a simple example. So here we're trying to compute this line integral over a contour that is the unit circle, oriented counterclockwise. So do I have a picture? Probably not. Okay. So that's a unit circle oriented counterclockwise, right? We give it the standard orientation, and we're going to integrate over, we're going to perform this integral. So first, what we can do is to compute the line integral directly using a parameterization of the circle. So the standard parameterization for the circle for being counterclockwise is you let x be cosine theta, y be sine theta. You take the derivatives, and so inserting this parameterization into, so you could kind of say like r of theta is equal to, and then you'd have these portions, right? For theta running from 0 to 2 pi. And so then inserting these into the integrand, we're trying to evaluate what the integrand is, or simplify the integrand before we actually perform the integration. So x y squared ends up being cosine times sine squared, and then dx is this minus sine theta. Then you have x times dy, which is there, and then I believe I just factor out. No, I don't factor anything. I'll just expand it out. Okay. Well, I factor d theta out. Okay. So then this line integral becomes this integral, and then you can proceed to integrate that. So nothing too bad here. This is just a u sub. This one, what happens is I've done a trig reduction, and then you can proceed to compute that, and you get pi as a result. Okay. So that is how you could perform this line integral directly. If we use Green's theorem, then Green's theorem says that that line integral is actually related to a volume, or no, an area integral, a two-dimensional integral over the circle, right? Over a filled-in circle. So I don't know, just a quick sketch maybe. So it's the filled-in circle. Now, so first, we compute what the integrand is going to be. So f1 is the first component function, f2 is the second component function, and then what you do is you take the mixed partials. So this one, well, you start with f2 sub x. So you take the x derivative of this, you take the y derivative of this, and you go ahead and you compute it. You get this, so that gives you that. And so the thing about this integral is there's a kind of clever way you can approach it. So maybe your reflex, and I think my reflex as well, would have been to convert this over to polar, because you can see that this is a polar region, right? This is a polar rectangular region. You could integrate r from 0 to 1 and theta from 0 to 2 pi. But if you do that, you also would make this guy a bit more complicated. This would be r squared cosine theta sine theta. You could certainly do the integral that way, but there's a little bit of a faster way to do this, which is actually it's mainly to do with this statement here, that the 2xy over this region, 2xy cancels by symmetry. So because the contributions when you have x being positive versus x being negative will give you that like slices, vertical slices to the left of 0 or to the right of 0 are going to be negatives of vertical slices to the left of 0. So they're going to contribute in ways that perfectly cancel each other out. And so that means that the double integral of this term goes to 0. And so once you see that, then you actually have the integral of 1 over this region, which is just the area of a unit circle, which is going to be pi r squared, which for r equals 1 is going to be pi. So you can actually very quickly get this calculation without necessarily doing this, which is, I've included this just to show you this is how you would do it if you want it, if you, I don't know, if you just for some reason wanted to do this in Cartesian coordinates. You would be able to. The bounds for y would be these functions, which you can kind of see. They are describing the upper hemisphere and the lower hemisphere of a circle. Integrating with respect to y, it becomes y squared over 2. The over 2 cancels with the 2 outside, and then you evaluate. And I think then at that point you get the symmetry property, maybe? I'm forgetting. I think it's an odd function in terms of x. If I substitute x by if I replace x with negative x in this expression, these terms, when evaluated, these terms will maintain the same sign, but this x will flip in sign, so this ends up being the integral of an odd function. Yeah, so maybe I can just label that. This is an odd function. With respect to x. And so that integral over a symmetric domain is going to equal 0. Okay. So that's another way to see it. All right. And so, right, all of this is to say that the double integral that we obtained from Green's theorem will also give us the answer pi. So both approaches have gotten the same value, and so we were able to verify Green's theorem for this this singular case. So I mean, it just gives you a bit of empirical proof, empirical evidence, I should say, of this result. So maybe you're slightly more convinced. Now let's take a look at this. So, okay. So we're asked to compute the circulation of this vector field over a triangular path with counterclockwise orientation, which is depicted by this picture. So I don't think I mentioned this in the line integrals section, but if you were to do this without Green's theorem, you would have to parameterize all 3 of these line segments and then add them together. That's because the total path C is comprised of these linear paths, which maybe you'd call C1, C2, and C3. These are all 3 different line integrals. You'd have to parameterize all of these, and then take those line integrals and then add the results. That would be the total line integral over C. That is certainly doable, but it's a bit tedious, as you can imagine. So instead, if we use Green's theorem, we can describe this as just one integral, a double integral, over this triangular region. And so we would opt to do that instead. So this, you take the x derivative of the second function, the y derivative of the first function, take the difference of them. So that ends up being this statement here. And, oh yeah. So this one is 0 because there's no y in there, and then this is 2xy cubed. Yeah, very good. So this line integral becomes this double integral, and of course, to set it up so that it's over this triangular region, you would do something like this, integrating on the outside from x from 0 to 2, and then for every specific value x, you integrate y from 0 to x. Right, so that sets up the integration over d, and then you go ahead and proceed to compute the this double integral. It's not too bad. Integral of y cubed is y to the 4th over 4, which then cancels with the 2 to give you 1/2. Evaluate from 0 to x. Do the evaluation. You end up with pull that 1/2 out. X to the 5th minus 0, so x to the 5th. And then you integrate that, x to the 6 over 6, evaluate from 0 to 2, and you end up with this. Oh, I didn't box it. Box. Oh, it doesn't It doesn't recognize. Okay, well, whatever. Um, right. Right. Here's a something that we can do. So we can use Green's theorem to compute the area of a domain by integrating over the boundary. So that, yeah, that's kind of interesting. All we need to do that, because, and I should just emphasize, because what Green's theorem is doing is it's giving us a correspondence between the integral over an area over some area D, some two-dimensional region D, and it's corresponding that to a different integral over the boundary of D. And so it's corresponding a double integral with a line integral. And now this is kind of an application working in reverse. We want to compute this double integral, but we're going to instead compute this line integral. All right. So what we need for that to work is we need it so that this difference that is part of Green's theorem, that this has to equal 1. And so it turns out there are 3 fairly common ways that you can make this work. You can, for instance, have the vector field like this, and you can check that for each of these that this is satisfied. Like, it's a pretty quick check, right? So this is just a partial with respect to x of x is equal to plus 0 is equal to 1, right? So, and I'm not going to bother going through it. But yeah, these three would all work. These three will all satisfy this identity. And so you can use any of them. Once you have that, then, well, this statement is Green's theorem. What we were trying to make happen was that this integrand was actually the function 1. We integrate that, which, well, as you should recognize, the integral of 1 is the whatever the corresponding volume is for that dimension. So when we integrate 1 in dimension 2, we're getting the area of the region. If it were a triple integral, it would be a volume. If it was a one-dimensional integral, it would be the length of the line segment or the length of the curve. Okay. Right. And now what we can do is we can plug these guys into this is it called the circulation form? I forget. But yeah, this form of the line integral. And so if you plug in the first guy, you end up with this expression. If you plug in the second, you end up with this expression. You plug in the third, you end up with this expression. So there's 3 common ways that you'll see this kind of formula show up. I believe that the OpenStax book only gives you this last one, but you can kind of notice that it might be a bit easier to use one of these two to compute area enclosed by some contour C. Okay. Right, and so yes, so this is the takeaway, right? These formulas give you a way to compute enclosed area by just using measurements along the boundary. All right. So here's an example of using this. We can compute the area of an ellipse. I guess this will be kind of a, well, no, this is just the general form of an ellipse by using a line integral. I'm trying to remember what is the other ways of doing this. I believe that there were other ways that were shown in like Calc 2 perhaps, maybe with like polar parameterization or something of that nature. But either way, like you should have come across the result, so you should be able to anticipate what the area of the ellipse is, which is this expression. So the idea is that with an ellipse you have say A and B. You have a major axis, which is and a minor axis. The major axis is the longer of the 2 ways that the ellipse is stretched. And so they kind of correspond to if you had a circle, right? If you had a circle, then you end up with both of the axes being the same length, r. And so, as you know, the area of a circle is equal to pi r squared. And so this is kind of just a deformed version of that, right? You still have the semi-major axis times the semi-minor axis. Right, the major axis is normally like the entire portion, and the minor is the entire portion there. So semi is to say it's half of that. So the A and the B there. So that's kind of how you could remember the formula for the area of an ellipse, is by relating it to the formula for area of a circle. Let's come back to the problem at hand. So what we can do to do this via a line integral, well, we can pick. Okay. So yeah, I've written all three. I've written the way to compute it using all three of the formulas here. Is my cursor showing up or not? Something has happened to my cursor. Okay, well, all right, that's better. Yeah, so all three of these. So using the first one, if you plug it in, and just to comment quickly, the parameterization is this. You can check that by plugging these into this expression. You end up with cosine squared theta plus sine squared theta equals 1. So that checks out. Yeah, so using this, x is going to be the a cosine theta. dy, you take the derivative of this function, and so you get b cosine theta. Then you perform this double integral. This double integral just gives you pi, or not double integral, sorry, this integral from 0 to 2 pi. This gives you just pi as a result, so you end up with pi times ab. If you instead use this other form, then you're doing minus y times dx. So minus y is going to be this negative b sine theta. And then the dx, take the derivative of this equation, you end up with minus a sine theta d theta. Minus a sine theta d theta, which is right there. You take the integral from 0 to 2 pi, and that just gives you, well, the integral gives you pi, so it's pi times ab, which agrees, so that's good. And lastly, if you have this 1/2 of this x dy minus y dx, well, minus y dx ends up giving you a... it's easier to see it from here, I think. So minus y dx includes all of this, the negative times the b sine theta times the a. And then x dy is this quantity, which you can see is the same. And so you'd perform this integral. Well, things simplify nicely here. A times b can be pulled out, and you have a cosine squared, and then these two minuses become a plus, then cosine squared plus sine squared, which is just 1, and so then this just gives you a 2 pi. And that cancels the 2, giving you pi ab. And so they all give you the same result, that the area of an ellipse is going to be pi times ab, a and b being the lengths of the semi-major and semi-minor axes. Okay, next let's talk about the additivity of circulation. Right, so I mean, I would mainly describe it from this picture. So if you have this region D and then you just decide to cut it into two smaller regions, that this would give you could talk about the circulation here, and you could talk about the circulation in this subregion and in this subregion. Notice that everything is oriented counterclockwise, right? But when we add up these two, notice that this path, which is labeled C middle, and this path, which is labeled C middle, these are the same exact line. It's running through the same points, but it's going through them in opposite orientation. And so that results in them canceling. So this is going through it in this orientation. Well, let me use a different color. So one of them is going through from left to right. One of them is going through from right to left. And the result is that these two cancel each other out. And so the circulation of D1 plus the circulation of D2 ends up being the circulation of D, which can be expressed mathematically in this form. Okay. Right. Now for a more general form of Green's theorem. So what was stated above with Green's theorem was that C, the boundary C, was a simply I believe it was simple. I forgot the phrase. Simple closed curve. Okay. Yeah, so it's a simple closed curve. Come on, where? My cursor. Oops. So, right. So before the boundary was a simple closed curve. Now we have some examples where the boundary is not just a simple closed curve. So for instance, in this picture, the boundary actually consists of two curves. It consists of C1 and C2. And notice that they are oriented in opposite directions. So this would be what I would call the standard orientation. So when you have a hole in your region, the holes have a boundary that is parameterized in opposite direction. There's a good reason for this, which I don't think I wrote here, but it is kind of expressed below. So we'll discuss that. But notice these equations. So the way that this is set up. So because this orientation is the correct orientation, kind of the standard orientation for D1, you end up having a plus for the C2. Whereas with this picture, notice that this internal, this hole has the correct orientation, but this has the opposite orientation. So in this case, you end up subtracting it. Okay. But for more general regions like this, regions that have holes, Green's theorem still holds true. So if you were able to set up a double integral over this region D1, you would also get the equality of comparing that against the integral over the boundaries D2. But because the boundary of the boundary of D1. So the problem is that the boundary of D1 consists now of two paths. So you'd end up having to create two line integrals, one over C1 and one over C2. And for this region, you'd have to create three line integrals, one over C1, one over C3, one over C4, and one over C5, which, if you orient this way, you have to introduce a negative. Okay. All right. Now, the visual proof, I guess, of the fact that this is the correct orientation is shown by this. So notice that what we can do is we can cut this region D through this hole so that the subregions end up not containing holes anymore. So now these regions are perfectly fine for the simple version of Green's theorem. And notice that along where we've cut, we would end up parametrizing it, well, in a counterclockwise fashion. So you can see that it both the parts that are part of the outer boundary and the inner boundary still have the same orientation in both of these parts, right? And that rather nicely we have these two. So when you connect these two together, the opposite orientations will allow those integrals to cancel. And so you just end up with the integral over the outer boundary and over the inner boundary. So because of that, we can say that this is oriented correctly. So contrast that with if this was oriented the other way around, we would not be able to do this. If we try to set this up, well, this is always going to be pointed in the wrong direction if this was also oriented counterclockwise. So in that way, we can regard this as the correct orientation. Yeah, and if it was oriented counterclockwise, that would be the opposite orientation. You'd have to just introduce a negative into the integral. Okay. Oh, something's going on with my scrolling. Let's see. All right. Now for the flux form of Green's theorem. So recall that what we were doing this kind of integral, f dot dr. So this kind of line integral, which we were also writing as f1 dx plus f2 dy. So if you can remember from the section on line integrals, we had this other line integral where what we do is we instead multiply by the normal vector into here, so that we end up capturing the normal component of the vector field rather than the tangential component of the vector field. This line integral is capturing the tangential portion component of the vector field. And so, well, we can do the same thing with, we can set up an analogous version of Green's theorem for that type of integral, that type of line integral. So, and of course that's going to compute the flux, right? So when we integrate over the flux version of the line integral, that computes the flux. All right, so in order to do this, you have to get to this statement. So the outward unit normal vector, n, has this expression, right? It's just quick derivation from taking the parameterization and normalizing it, and then recalling that in order to get from the tangent vector to the normal vector, you have to rotate by 90 degrees, and you can see in this picture you rotate it counterclockwise, and so that will result in swapping these two and introducing a negative into the second component. And you can check that, that this dot that is going to equal 0, so everything works out. So then the flux, the flux integral, if you go through it and you simplify things out, you'll end up with this expression, which then becomes this. So now that we have it set up like this, notice that we can view this as as the kind of line integral that is accepted by Green's theorem. If we put that negative next to the f and we have a plus here instead, well, and also then we have to swap both of these terms. So the point is that we're kind of comparing it against this, which is what Green's theorem set up for us. Green's theorem said that this, with respect to d, was equal to f2 dx minus f1 dy all dA. Okay, so we're basically going to take this and fit it into this format, and if we do so, you'll see that you end up getting this expression. I'm not sure if it's completely clear to see. It's a little hard to keep track of, but you end up swapping this term and that term. So, I'm not sure if I want to do this. Let me call this G1 and let me call this G2. So if we do that, then according to Green's theorem, this ends up equaling. So we view this as plus g1 dx plus g2 dy. And then so that allows us to insert that in. So we end up with a partial g2 dx minus partial g1 dy, all integrated with respect to a. But now, notice that this is actually, when we sub back the g's for the f's, then you end up getting f1 dx minus, and this should be negative, yeah, so minus negative f2 dy. So that becomes a plus. So that's how we end up with this expression. And so that gives us the flux form for Green's theorem. Right, so this is the flux form for Green's theorem. I don't think that that's on your homework, but well, it's worth mentioning that it's there. So just in case you come across it, or in case you end up needing it. All right, and so some last remarks about this. So once we talk about divergence and curl, which I think is the next section. Yes, this is the next section. So once we have divergence and curl, then we can actually reinterpret these formulas. So we had these two formulas. So this is the typical form, or the circulation form of Green's theorem, and this is the flux form of Green's theorem. Right, this formula we just derived, this you can check from above, that is the formula. The idea is that once you have divergence and curl, well, you can actually recognize that this is the z component of the curl of the vector field f, and this is the divergence of the vector field f. So we'll see that. You'll see that shortly. You'll see that once you know what divergence and curl are. And also a bit of a comment looking forward as well. Green's theorem is effectively a flat version of Stokes' theorem. Okay. Or in other words, Stokes' theorem generalizes Green's theorem. So with Green's theorem, we were subjecting ourselves only to surfaces that lived on the the xy plane. They were always flat. They were always on this xy plane. Stokes' theorem is going to lift us up to the third dimension. And, well, technically it goes beyond the third dimension, but we're only going to work with the third dimension in this course. Where what you have is you have a two-dimensional surface, say, well, I'll try to draw a picture of it. So you might have, oh dear. That's not good. All right, well, close enough. You might have that. I wonder if I can. Do I even need that? I don't think I need that. No. Just so think of a upper hemisphere of the unit sphere. So you have. I'm not very good at illustrating things. I'm trying to represent that you don't have the inside, you only have the outside. So think of this as like being hollow, or just as being a membrane. And so the two-dimensional region would be the boundary of this upper hemisphere. Did I say boundary? The two-dimensional region is this upper hemisphere. The boundary is the lip down here, which is just the circle. So Stokes' theorem would work for such a region, whereas Green's theorem would only work with, say, the disk that lives on the plane. It would work. So Green's theorem would work if it was flat, like that. But instead, we have this shape where we've kind of puffed it up to the third dimension. Okay, I guess that's it.